Today we're going to go over our first sorting algorithm, which is going to be bubble sort. So what is bubble sort? Bubble sort compares pair of adjacent values and then it swaps the two values if they are not in order. So it's going to look at two numbers, it's going to swap if not in order. And there is a way to optimize this code or this operation, which we will go over later, but just know that if everything is already sorted, we don't need to sort it anymore. And I'll illustrate that with an example. Let's say that we have an array, so -2, 2, -1, 1, 0, and 0. So this array covers positives, negatives, and duplicates. All right, let's see how the sorting is going to work. Let's copy down our array one more time. Okay, so first thing it's going to do is it's going to start at index 0, and then it's going to compare its adjacent element, which is the next value. So it's going to compare 2 and -2, or -2 and 2. Well, are these two numbers sorted? Yes, because -2 comes before 2, so it's not going to do any swap. So it returns that same array, and then it's going to check 2 and -1. Well, are these sorted? No, it's not, right? So it's going to swap, and then it's going to return that new array, which is going to be this array, and then it's going to look at next two values, so 2 and 1. Are these in order? No, it's not, right? So it's going to swap again. So do you see the pattern here? Now it's going to check 2 and 0. Obviously, these are not swapped. So we get, all right, now our finally last iteration is going to compare 2 and 0. And obviously, this is not in order. Okay, so after our first whole iteration of this array while comparing two adjacent values, so we got this array as our result, but obviously this is still not sorted, right? So think of this whole iteration as our outer loop where I is equal to 0, and then our inner loop as j is equal to 0, j is equal to 1, j is equal to 2, j is 3, j is 4, and j is 5 here. So we have our nested loop, and we were able to at least sort this one number, which is 2. We don't know about other numbers yet. Well, actually the computer doesn't know about other numbers yet, but we know for sure that this last number is sorted. Now it's going to do that whole iteration one more time. So this time I is equal to 1, and let's bring our array -1, 1, 0, 0, 2. So you can see that this is almost sorted, but remember, computer doesn't know that. So if we were to go through this one more time, it's going to be comparing -2 and -1, which it did not change, so it's not going to do anything. Now it's going to compare -1 and 1, which it did not change because it's sorted already. And so if we go through the whole process, this is what we get. You can see that our result is sorted, but remember, computer does not know if it's sorted or not. And one thing you have to also notice is that, remember, our 2 is sorted, but now our 1 is sorted. So we know that we actually don't have to run this last inner loop. So this is one way we can optimize our solution, right? So let's consider that when we code our solution. And since computer doesn't know that this is sorted, it's going to do the next operation. I is equal to 2, I is equal to 3, and so on and so forth, until we get our final result, which is going to be -2, -1, 0, 0, 1, and 2. But computer is going to keep checking, is going to keep looping through our nested loop to check if these are all sorted or not. So once we know for sure that our array is sorted, there is actually another way to optimize, and we will go over that one more time in our solution later. So I think I'll go over the solution in 3 ways. First one is going to be unoptimized, so not optimized. Second one, I'm going to optimize a little. And our last one is obviously going to be the best solution, which is going to be optimized perfectly. But for purpose of this, just know how the swapping and our nested for loop works and how it sorts our values. That's more important. So think about that logic and try to code on your own if you can. If you guys find this helpful, make sure you guys like and subscribe. Thanks. Now, before coding our solution, I want to go over this two functions, and it's called swap1 and swap2. So essentially, they're doing the same thing. It's just that this second one is ES6 version. Now, what does these functions do? It's simple as what the name suggests. It simply swaps two numbers in an array. And as you can see, it takes three parameters: array, index 1, and index 2. Now, say that we have our example array of 1, 2, 3, and 4 and 3. And this one is obviously not swapped, right? And if we were to call our function swap array 2 and 3, is going to return something like 1, 2, 3, and 4. Now you can see that it's swapped, right? We are swapping array at index 2, this one, with array at index 3. And as a result, we get this array. But do notice that these two functions are just helper methods. It actually doesn't return an array. Array is going to be returned by our bubble sort. Now let's go over our code just to get a better understanding. Let's go over our first one because this better illustrates how the logic works. So first thing is going to be we are storing first element to temp variable. And this we are going to use later. We use this later. And second one, what are we doing here? We are overriding our first number with the second number. So let's say that temp is stored of a number 4. And this second line is overriding our first number, which is 4, with our second number, which is 2. So override first element with second element. And if we were to do that, how would our array look like? So it would look like something 1, 2, 3, and 3. Because remember, 3 is our second element, and then 4 is our first element. So when we override our first element with the second element, we are going to have 1, 2, 3, 3. But our second line, what does this do? It's overriding our second element with our temporary variable. And what is our temporary variable? It stored the first element, right? And remember, I said that we are going to use this again later, and this is where we are using it. So now what's going to happen? It's going to be 1, 2, 3, 4, because this 3 is overridden with this temp variable. So actually it's something like temp, which temp was equal to 1, 2, 3, and 4. So this is pretty much the step what the code is going through. And this one is obviously simplified with ES6, but the logic of swapping function is better shown by our first one. So first thing, again, we store our variable to a temporary variable. Second, we override our first element with the second element. Third, we override our second element with temporary variable, which was equal to 4. So let me finish writing our pseudocode or comment. Override second element with temp variable, which was equal to first element. Now that's how our swapping function works. So think about how this works. This is really important, and you are probably going to use this a lot when you go over other sorting algorithms. Now let's go over our first iterative unoptimized solution. And why are we going over a unoptimized solution? Well, it's because I want to show how the process of optimizations work. And if you were to do things one by one, I think it helps you understand the logic of bubble sort better. So I think it's good. And if you can stay with me and go through the whole thing, I think it'll be very beneficial. If not, you can just go through the solutions or whatever solutions that you want to look at. Now let's go over our pseudocode. This is our pseudocode, and you can read it, try it on your own. If you can try it and get the solution without looking at the pseudocode, that'll be awesome. That'll be really good practice for you. But if you didn't get it, that's fine, because we're gonna code it. So first thing, let's go over our pseudocode. Step 1, create a function named BubbleSort which takes in parameter array. So we are going to make a function named BubbleSort, and that's going to take our array. Second, we are going to iterate through our array and then repeat comparing and sorting elements. if you remember from our illustration, we had to make a nested loop for our sorting element to work. So if we didn't have a sorting element, we would have only one element that's sorted for sure, 100%, which is going to end up at the last index. And that's why we need a nested loop to keep iterating through our process of sorting and comparing. Next is we're going to have our inner loop, and this is also going to compare and sort elements. But in the inner loop, I'm going to create a temporary variable to store my current element. So this is pretty much a part of our swap function. And then I'm going to check if my adjacent element is less than my current element, I'm going to swap. And I'm going to keep doing that until I have my sorted array. And finally, I'm going to return that array. Now let's start coding. So for let I is equal to 0, we're going to start at the first index. And we are going to iterate till I is less than array dot length and increment by 1 each time. Nice. Second, we're going to have our nested loop. J is equal to 0 and J is going to be less than array dot length and increment J by 1 each time. Now, our third step, we want to make a variable named temp and store that with a current element. So it's going to be J. Alright, now it's going to be our if statement, but I want to first return my array. And obviously it's going to return the same array right now because we didn't do any swaps. So I'm going to check. This is the most important part. If my adjacent element is smaller than my current element, I want to swap because that means that it's not in order. So let's look at it. For example, my current element is going to be -3 and my adjacent element, or let's simply call it next element, is going to be just 3. Well, is 3 smaller than -3? No, it's not. So our if statement isn't going to run and we don't have to do any swaps, right? But then we loop through our second array or second pair of values, which is going to be 3 and -2. Well, is -2 less than 3? Yes. So we are going to swap these two numbers and we are going to have -3, -2, and 3 as our new array and the rest of the elements. So let's write that with code. So if my adjacent element or my next element, which is represented by array at index j plus 1, array at index j plus 1. Well, this makes sense, right? It's array at index j plus 1 because array j is going to be, oops, this should be 0. Our array j is going to be index 0 and j plus 1 is our adjacent element, which is going to be 3. So as our adjacent element is less than my current element, what am I going to do? I'm going to want to swap. And if you remember our swap function, how does it look like or how does it work? So first element, array at j, is going to be equal to the next element. So array at index j plus 1. Okay, that looks good. Now it's going to be array at index j plus 1 is going to equal to our temp variable. And we are done with our code. So that should give our result, which we got over here, and it looks good. But now let's go over our if statement again, because I think this is the most confusing part. So j plus 1 is our next element or our adjacent element, and array at j is our current element. And again, if my next element is smaller than my current element, I want to swap. And we are doing the swap over here. But remember, we had a separate function for swap. So you can actually make a swap function inside this function and then just call swap here. So if I were to illustrate that, let's just do our swap function in ES6. So const swap is going to take 3 parameters, array, index 1, index 2. Okay, looks good. And then it's going to be an array at index 1, comma, array at index 2. And that's going to equal to array, index 2, and array, index 1. Alright, that's our swap function. So if we had our swap function inside this, we don't need this temporary variable. We don't need these 2 lines, but I won't delete it. I just want to keep it here. And I just have to do a swap. Well, we're going to pass in our array, right? Array, that won't change. And I want to pass in 2 indexes, which is going to be j plus 1 and j. And order doesn't matter. You can do j plus 1 and then j, or you can do j here and then j plus 1 here. and something is wrong. Index is not defined, so this should be index 2. I hope you caught that. And as you can see, we get our same result. Alright, now we're pretty much done with our code, but let's see how this code actually works. So I'm going to console log array. Okay, so as you can see, we have our initial array, and the first iteration, it did not make any swaps because -3 is smaller than 3. And then we compare the next two elements, which is going to be 3 and -2. And obviously -2 is smaller, so we got our result here, which it made swap, so -3 and -2. And it's going to do that for our whole array. But when we do our first iteration of our outer loop, so our I for loop, and you can see that number 3 is sorted. So we know for sure that at least one number is sorted. And as we go through, we keep swapping, we check, and you start noticing that our array doesn't change at all for like at least good half of the results. So how can we avoid this? How can we avoid unnecessary checkings or iterations from our loop? We are going to cover that after we code our recursive solution. And recursive solution isn't going to be the best, but it's interesting to see a different solution just for practice. I think you'll learn a lot from it. So let's go over that and start optimizing our solutions later. Now let's go over our recursive solution first. We're gonna go over this one first because I think it's just interesting to see a recursive solution as to working on a iterative solution. And after this, we are going to optimize our first solution that we made. So if you remember, our iterative solution had a space complexity of O of 1. And why is it O of 1? Well, it's because it's not really making any other extra variables other than that temporary variable that we made to store our current element. But space complexity is going to have a O of n. And if you remember from our space complexity video, you will probably figure out why this code is going to have a space complexity of O of n. If not, we'll go over it again probably after we code our solution. Now we have our pseudocode. We are going to make our function which takes in two parameters, array and length of array, and we are going to create swap function. I think you should be pretty well versed with this by now. And then this is our base case. If length is equal to 1, we are going to return our array. And now we are going to make a for loop, and we are going to iterate array minus 1 times. And the reason why we iterate array minus 1 times is because say that our current element is the last element. Do we want to check the adjacent element? No, because our adjacent element is not defined. That's why we loop it array minus 1 times. So this is small optimization or correction to our previous code. And then we want to check if our adjacent element is smaller or greater than our current element. And if it's in the wrong order, we want to swap. And lastly, we want to recursively call our function to sort our array. And then we're going to decrement length by 1 each time. All right, first thing, I'm going to create my swap function. And let's use temporary variable this time to make our swap function, not EX6 version. So it's going to take an array, index 1, index 2, and this is pretty much repetition, so you can skip over this part if you like, but it's a good practice. I'm going to make a variable. Temporary is equal to array at index 1. And I'm going to overwrite first element with the second one. Next thing is overwrite my second element with the first element, which was stored in my temporary variable. Okay, I think this should be really straightforward. So now I have my swap function and I want my base case. So if length is equal to 1, I am going to return my array. Okay, and next I want to iterate through my loop or my array actually. So starting at index 1, I want to iterate till array.length minus 1. And why is it minus 1? Again, it's because when our current element is the last element, we don't have an adjacent number. So that's why we do it until here. And our adjacent number is this one, the last element right here. And let's check. Now we need our if statement. So if current element array at index I is not this one. If my adjacent element is smaller than my current element, so they're out of order, what I'm going to do is I'm going to swap, pass in the array, pass in the index and my other index. And finally, I'm going to recursively return this function, bubble sort, and it's going to take in array, and I'm going to decrement length by 1. It should be bubble sort. Okay, we have our solution. So as we can see, we have our array sorted -3 till 3. So it looks good. But how does this differ from our first iterative solution? Well, our inner loop is pretty much the same. So think of this one as our inner loop. And our outer loop is pretty much this. So think of this as our outer loop where length is decreased by 1 each time. And this is going to run how many times? Of n number of times. Why? Because, well, if you look, we are decrementing length by 1, right? So what does this do? Well, it's going to run obviously of n number of times. And when it hits our base case, it's going to exit out of those recursive calls and then give us the result that we want, which is the sorted array. And obviously the reason why we have O of n is because we are running this again until length number of times, which is O of n. Now let's go over our optimized solution, but this is still not the best optimized solution. And the reason is because remember that when we go through our array, and we remember we had a nested loop, right? When we do the first iteration of one whole sorting, you notice that at the end, at least one number is going to be sorted, right? So when we compare -3 and 3, -3 and 2, and so on and so forth, when we do that comparison and sorting, we know that 3 is going to end up all the way at the end. And you don't know about, or actually the computer doesn't know about what happened or how the rest of the numbers are sorted, but it knows for sure that the last element is sorted. We know that the biggest number is going to end up at the last index. And when we do one more sorting of this whole array, we know that 2 is going to end up at index over here, and we know that 2 numbers are going to be sorted. So that's a hint as to how we can optimize our code. So let's look at our pseudocode. The create function named bubble sort, it's the same. We are going to iterate through our array, which is going to be the same, but our nested loop is going to be a little bit different. And to be honest, this is the only thing that's different. This is going to iterate until j is less than array.length -1 minus I. So this I represents number of elements that are sorted. Again, for the first iteration, we know that one number is sorted. Second iteration, another number is sorted. And then next iteration, another number is going to be sorted. So we know that we don't have to look at this number because it's sorted. So let's take that into consideration and code our solution. And if you can try it on your own because it's pretty much the same thing as before. So I is going to be less than array.length, increment by 1 each time. Going to have another loop, j is equal to 0. And remember, this part is important. J is going to be less than array.length -1, and you remember why it's -1, right? And minus I, and then we're going to increment j by 1 each time. Next, we are going to have our same if statements. So if our adjacent is less than our current value, what we're going to do is we are going to swap. Do you remember your swap function? We will use ES6 version this time. So j plus 1 array at index j, and this is going to equal to array at index j and array at index j plus 1. Okay, it looks good. Now let's return our array and you should have that same result. So the key point to take away from this optimization 1 is that we can just ignore or subtract index I because we know that as this outer loop runs each time, we know for sure that at least one number is going to be sorted. And when it runs one more time, one additional number is going to be sorted. So we don't have to look through these two numbers. Now we are going to finally implement our most optimized solution for our bubble sort. And we are going to use do while loop to do just that. And if you're not familiar with what do while loop is, is pretty much same as our while loop, but it differs on one thing. It ensures that whatever our code is, it's going to run at least once. So do while statement creates a loop that executes a specified statement until the test condition evaluates to false. So this is pretty much the same as our while loop. It's going to run until the test statement is going to evaluate to false. But one critical different fact or characteristic of do while statement or loop is that condition is evaluated after executing the element, whereas while loop evaluates the condition before executing the statement, resulting in specified statement executing at least one. So it's saying that our code is going to again run at least once, and then it's going to evaluate our condition whether if it's true or false. And this is optimized because the code runs as long as the numbers are swapped. So just to illustrate the difference between while loop and do while loops look something like this. While we have a condition and assume it's going to do something, right? Whereas do while loop is going to look something like do while, and our condition is in here, condition, and we are doing our execution or whatever our code is, something here. So while loop first checks the condition, and if it's true, it's going to do something. But do while loop is going to do that code, is going to do something, and then it's going to evaluate our condition. So this is the key difference between while loop and do while loop. So that's it for our intro to do while loop, and let's code our solution. So we have our pseudocode, and obviously this pseudocode is going to be different from our previous pseudocodes, but pretty much the concept is obviously going to be the same. We're going to create a swap function. We're going to declare a variable named swapped, and this is going to check if we swapped or not. And we're going to declare another variable, and we'll name it I. And we are going to set it to -1 or -1. And this is going to keep track of number of sorted numbers. Remember, we did array length -1 minus I times, and you should know the reason why we are doing this by now. We talked about it many times. But important thing is, why are we setting our I variable to -1? Well, that's because when we code our solution, we are going to first increment our I. Remember, do while loop runs at least once. So when our code runs, we are going to increment our I variable first, and that's going to set it pretty much equal to 0. And then inside our loop, we're going to set swap to false. We are going to increment I by 1, and we are going to iterate through our array -1 minus I times and check if our element is less than or greater than our current element. Swap, if it is true, swap, and then we are going to set swap to true so that we can run our while loop again, and then finally it's going to return our array. So first things first, let's declare our variables. So let swapped, I'm not gonna set it equal to anything, and I'm going to make my I and set it equal to -1. And let's make our do while loop while it's swapped. So as long as swapped is equal to true, we are going to run our function. I am going to set swap to false, and I'm going to increment I by 1. Now let's make our for loop so that we can iterate through our array. Let j is equal to 0. J is going to be less than array dot length -1 minus I, and we are going to increment by 1 each time. So inside our for loop is pretty much gonna be the same as always. So if array at index j plus 1, so if our adjacent number is less than our current number, what are we going to do? We are going to swap, and we are going to pass in our array. We're going to pass in our index and the next index. Well, one thing different about this is that when we swap, we want to set our swapped variable to equal to true. So swapped is going to be true. And finally, we are going to return our array. And as you can see that we got our result. It's sorted. But more importantly, I want to go over our code one more time. So we declare two variables, swapped and I. I is equal to -1 because when we run this do while loop at least once. We know for sure that this is going to run at least once. We are going to set swap to false because we're pretty much setting a default value of swap to false over here. And we're incrementing I by 1 so that this will become 0. And we're iterating through our array, and we are doing -1 because if our current element is at index over here, we don't have an adjacent element. So that's why we're subtracting 1, because we want to stop when we are checking our current element of this one and our adjacent element is the last one. And again, we are subtracting I because we know that as we go through our loop, we are going to sort one number and the next iteration, or sort another number, and so on and so forth. So pretty much do while loop is kind of like our outer loop, obviously. And then we are going to increment by 1. Next, we do our check. If our adjacent number is smaller, we swap, and we are setting our stop value to true. So this becomes true now, and we are able to run our while loop one more time. And this is going to keep repeating until we have nothing to swap. And if I were to just console log how many times our do while loop runs, so let's just console log swapped. Okay, so we actually made an error for our code, and I hope you caught that. It was because of this. We're incrementing j, not I. So again, if we were to console log swapped, I thought I did something wrong. You should see that it's sorted again, and this ran pretty much 3 times, right? Because true, true, and true. So you can see that our outer loop did not run array length number of times. So we were able to cut down our operations pretty much a lot. And next, let's just compare how our bubble sorts work as we optimized our code. Now, this is our first iterative solution, which was unoptimized. And for all the iterative solutions that we made, I declared a counter variable. I incremented counter by 1 each time the iteration worked or iteration ran. And finally, I console logged counter just to see how many times it compared and sorted elements. And as you can see that this first one ran 64 number of times. And if we were to look at our second one, I have my counter variable, I'm incrementing my counter, and finally just printing a counter. And this one pretty much did less than a half of our first solution. So it is optimized, right? But if you look at our last one, you can see that we did 22 number of comparing and sorting for our most optimized solution. So this is pretty much a third of what our first solution was. So you can see that as we optimize our code, this comparing and sorting of our array using bubble sort did less and less job. But we are able to get pretty much the same output. Now let's look at our time complexity. So best case is O of n, and this is when our array is sorted and there is nothing to sort. But why is it O of n? Well, it's O of n because we at least have to go through our array comparing each one to check if it's sorted or not. That's why it's O of n. And average is O of n squared if it's mixed, and worst is O of n squared. So this is if the case was that if it's our original was in descending order, but we want our array to be in ascending. So you would have to do every single comparison and sorting for all the elements. And space complexity is O of 1 because we are just simply making a temporary variable to store the current element, and there's nothing else that's used. And this is O of n for our recursive solution, and we ran over the reason why when we coded our recursive solution. But overall, space complexity is going to be O of 1, and worst time complexity is going to be O of n squared. Now, this is a bonus lesson or bonus practice that you can do on your own just to check what you learned today. So we're going to implement our bubble sort using the optimized solution, but our solution is going to be descending order. We are going to sort our array in descending order. And this is our pseudocode. It looks pretty much the same. If you can do it without it, try without it. That's great. If not, that's totally fine. So first thing I'm going to do is declare a variable named swapped and declare I to check how many elements are sorted. Set that equal to -1. And I want my do while loop now. So do while swapped. I want to finally return my array. Okay, so that looks good. I want to set swap to false, and we're not redeclaring our variable, and I want to increment I by 1, and now my inner loop. So inner loop, let j is equal to array dot length minus 1. So I'm going to start at the end, and j is going to be greater than 0 as long as j is greater than 0, and I'm going to decrement by 1 each time, and it shouldn't be I, it should be j, and I'm decrementing, so it should be j minus minus. And remember, one more thing, we are supposed to subtract how many numbers are sorted, and that's represented by the variable I. So we are going to do j minus I. And now we need our if statements to check if the numbers are sorted or not. So it's going to be array at index j plus 1, right? So j plus 1 is less than array j. Well, this is actually wrong because array j is going to be represented by our last element. So we need this number to compare. So because we're comparing this one and this one, and then we're comparing this one and this one. So we need the previous element. So that's going to be array at index j minus 1. And we want our swap function. And swap function is going to look like array j minus 1 and array at index j. That's going to equal to array at index j, and array at index j minus 1. Okay, that looks good. And finally, we want to set swapped to true because we just swapped the number. And as you can see that we have our descending sorted array.